Hi everyone, and thank you for joining us. Today I will present our work, Aerial Optimized Hybrid Quantum Convolution Neural Network for Epileptic Seizure Detection in EEG signals. This study was conducted by Stephanie Paso from Mississippi State University and Ronald Ho from UC Berkeley. The central idea is straightforward. Instead of manually designing the quantum part of a hybrid EEG classifier, we use reinforcement learning to search for a compact circuit that performs well. I will briefly cover the clinical motivation, our QGDD framework, the experimental results, the current limitations, and the next step. Epilepsy affects roughly 50 million people worldwide, so reliable seizure detection has a very broad clinical impact. EEG is one of the main tools used for diagnosis and monitoring, but manual review is time-consuming and can vary from one specialist to another. The chart on the right illustrates a broader concern in this field. Models can report very high performance on controlled benchmark, yet perform much less reliably on large real-world clinical data. For example, the literature reports near-perfect results on small benchmark settings, while one deep CNN study achieved only 30.8% sensitivity on the DUH-EEG corpus. These are not identical experiments, so comparison is illustrative rather than one-to-one, but it clearly shows the generalization gap we are trying to address. Classical methods have made important progress, but several limitations remain. Traditional machine learning models usually depend on handcrafted features, which means performance is closely tied to expert feature design. Deep CNNs can learn features automatically, but they often require more training data and can overfit when the clinical cohort is small. On top of that, EEG patterns vary substantially across patients, recording device, and acquisition conditions. So the real challenge is not simply achieving a high number on one benchmark. We need models that are accurate, parameter efficient, and better able to adapt when the data distribution change. This is where quantum computing really shines, offering some exciting advantages. Quantum computers can process data in these incredibly vast space using things like superposition and entanglement. This means they can find patterns that classical computer might miss, and they can do it with far fewer meters. We are seeking that hybrid quantum classical models can give us competitive performance with much less complexity. So, this quantum advantage could be key to overcoming the limitations of classical methods, leading us to our new framework. Our solution is called Quantum Gate Dynamic Design, or QGDD, and it's pretty innovative. We've got a reinforcement learning agent that actually designs the quantum circuit itself, which is a big deal because it takes out all the manual guesswork. It combines a classical CNN for initial feature extraction with a dynamic quantum layer, all trained end-to-end. Our main question is whether this RL-optimized QCNN can actually beat the static, manually designed one. Next, we will dive into the dataset we use to test this. So, to test our QGDD framework, we use the bone EEG dataset, which is a really common benchmark in seizure detection research. This dataset is super important because it lets us evaluate our framework across different clinical difficulties. It has 500 EEG segments split into 5 subsets covering both healthy and epileptic patients. Each segment is pretty long, about 23.6 seconds, giving us 4,096 data points per sample. We then tested our models across 9 different classification scenarios, from simple binary text to more complex multi-class problems, using a standard 70-30 trends test split. This thorough evaluation helped us understand how well our model generalizes. Now let's dive into how our RO agent actually works to optimize these quantum circuits. Building our dataset, our RO agent is the brain behind optimizing the quantum circuit design. We frame this whole process as a Markov decision process, or MDP, which basically means the agent learns by making a sequence of decisions. Agent actions involve things like adding, removing, or changing quantum gate in the circuits. The cool part is the reward function. It's not just about accuracy, but also about keeping the circuit shallow and computationally efficient. We use proximal policy optimization, or PPO, to guide the agent, aiming for the best accuracy with the least complexity. And this iterative process allows agent to discover optimal architectures on its own. Next, we will look at how this RO optimized quantum circuit fit into our overall hybrid model. This diagram shows the complete architecture search loop. At the top, the PPO agent receives the current quantum circuit and chooses a structural action. The environment applied that action to create a new candidate circuit using rotation gates, RY, RZ, and RX, and CNOT entangling gates. The hybrid model builder then combines the circuit with the classical EEG pipeline. The CNN uses convolution, batch normalization, pooling, and global average pooling, followed by a 4-dimensional embedding. Embedding is angle encoded onto 4 qubit, processed by the candidate circuit, and measured on all 4 qubit. A small dense head produces the final class probabilities. The architecture evaluator trains the candidate for a short proxy run, measures accuracy, depth, CNOT count, and time, and returns a scattered reward. The PPO policy is updated, and the loop repeats. In our experiment, this research ran for 4,000 time steps, or about 608 episodes. So, after the RO agent figure out the best quantum circuits, we integrate it into our hybrid QCNN architecture. This model is pretty neat because it combines the best of both worlds, classical and quantum computing. We start with a 1D CNN, which is a classical component to extract initial feature from the raw EEG signal. Then this feature go into our personalized quantum circuit, which the RO agent designed to pick up on those really subtle, high-order interactions in data. The whole thing is trained end-to-end, making sure gradient flows smoothly. This hybrid approach gives us competitive accuracy, but with way fewer trainable parameters, like only about 745 in the quantum layer. It's all about getting that quantum expressiveness without sacrificing efficiency. Now let's see how this hybrid model actually performs. Now for the exciting part, the performance comparison. Our RU optimized QGDD really shine here, outperforming the static baseline QZNN across the board. We saw consistently higher classification accuracy in all 9 scenarios, both binary and multi-class. This means it's better at telling the difference between healthy and epileptic signals. Plus, we got improved sensitivity and F1 score, which are super important for correctly identifying seizure events. The best part is that this automated architecture search significantly cuts down on the manual effort usually needed to design this quantum circuit. And it does all this while keeping the model complexity competitive, proving that automation doesn't mean sacrificing efficiency. This really showed the power of RL in optimizing quantum models for seizure detection. So what does all this mean for the future? Let's talk about our contribution and next step. Well, this is the best circuit discovered by the agent, the blue RY gates. On the left perform the initial angle encoding. The learned architecture then used 3 CNOT gate and 5 parameterized rotations. One interesting pattern is that agent plays uh, entangling operations early before most of the trainable rotation. That allows the later rotation to act on already correlated qubit states rather than on independent qubits. Qubit 0 also acts as an information hub because it participates in multiple entangling interactions and receives 2 RY rotation. Finally, the RZ gate on qubit 3 introduces a phase degree of freedom. This entanglement-first topology was discovered automatically. It was not built into the search as a preferred template. The radar part compares the static baseline in blue with QGDD in orange across all 8 binary scenarios. The proposed model is better in 6 scenarios, ties the baseline on S versus Z, and trails it on S versus O. The largest gain is on S versus F, where accuracy improves by 8.33 percentage points. We also see gains of 6.67 points on S versus ZONF, 5.3 points on ZO versus NF, and 4.444 points on S versus NF. These pooled and seizure-related tasks contain more heterogeneous signal patterns. So the broader orange profile suggests that the discover circuit is especially useful when the class boundary is more complex. This table gives the complete scenario by scenario result, and it is the most important slide for interpreting the model fairly. Overall, QGDD match or outperform the baseline in 7 of the 9 scenarios. It reached 100% accuracy on S versus Z, S versus N, S versus F, and S versus NF on a clinically relevant S versus Z O NF task, seizure versus all non-seizure groups. Accuracy improves from 92% to 98.67% on ZO versus NF. It improves from 89.17 to 95%. However, the method is not universally better. The baseline performed better on S versus O, and on the 3-class SOF test, QGDD reached 76.67% accuracy compared with 83.33% for the baseline, with sensitivity dropping to 46.67%. A likely reason is that the IO search was optimized on the binary task, so the discovered decision structure does not transfer as well to the more demanding multi-class setting. This motivates scenario-specific or multi-objective architecture search in future work. So to wrap things up, our work makes some pretty significant contributions to the field. We introduced this novel QGDD framework, which automates the search for optimal quantum architecture, moving away from manual design. We also developed the first IO-optimized QCNN specially for epileptic seizure detection, showing that this approach can achieve higher accuracy and sensitivity than traditional methods, all while keeping the model neat. This really lays a strong foundation for quantum machine learning in healthcare. Looking ahead, we want to test our framework on even larger and more diverse EEG dataset to really prove these generalization capabilities. We are also excited about implementing this on actual quantum hardware to see its real-world potential. And finally, we think this QGDD framework can be extended to other biomedical signal classification tasks, opening up a lot of new possibilities. Thank you for your attention. Our contact information and LinkedIn link are shown here, and we will be very happy to take your question. Thank you.